Okay, I'm going to do lab differently today. What we're going to do is we're going to go through the lab together in sync. So I just decided to change it completely. So um, what we're looking at today is ammonium chloride. Ammonium chloride in pure form, what do you think it is? Solid, liquid, or gas? Pure ammonium chloride. Ammonium chloride is salt. The salts are these ionic compounds that aren't acids. And so if we think of most salts, like sodium chloride, etc., or ionic compounds like calcium carbonate, most of them are solids. Yeah. In fact, I really can't think of any liquid or gaseous salts at room temperature. So ammonium chloride, salt. Is ammonium chloride soluble or insoluble in water? Soluble. Ammonium and group 1 salts are all soluble. So if I have some water around, I can dissolve this in water, and that forms ammonium chloride aqueous. Is ammonium chloride aqueous a strong electrolyte, weak electrolyte, or not electrolyte? Well, weak electrolytes are the weak acids, weak bases, and some heavy metal salts. Mercury. But strong acids, strong bases, and the soluble salts are classed as strong acids, strong bases, and soluble salts are classed as strong electrolytes. What strong electrolytes do is what? Strong electrolytes do what? I'm sorry? They do conduct electricity. How come? They conduct electricity because they're mobile ions in solution, mobile charged particles. They have translational motion. And so ammonium chloride, if we have a unit of this, it's not charged. But if I break it up into the ions, then I have charge. And so strong electrolytes ionize or dissociate 100%. That's what we know. So ammonium chloride is a white solid. You can take this white solid, dissolve it in water to form an ammonium chloride solution. The ammonium chloride solution consists of ammonium ions and chloride ions. Now let's look at the chemical properties of ammonium. What are some chemical properties of ammonium? So one of the first chemical properties we probably consider this. Ammonium is an ion. So we think of what other ions is ammonium like? What other ions would ammonium precipitate with? Now, if we're looking at some ions which are bases, we can consider that in the acid-base part. No, metathesis. If we look at metathesis, what precipitates with ammonia? Anything? Actually, nothing does. There's no metathesis reactions. And then we could go to acid-base. In terms of acid-base properties, which category would ammonium fit into? Would it be an acid, base, or neutral? An acid, yeah. Exactly, yeah. And this will react with all bases stronger than NH3. That's good. And so we have anyway, would this be, what do you think? A weak acid, strong acid? What do you think it is? Weak acid or strong acid? It's a weak acid. And weak acids are also weak electrolytes. And so weak electrolytes do what? Well, strong electrolytes break up completely. The weak electrolytes, yeah, they stay together, but a little bit breaks apart. And so if I have ammonium, ammonium is a weak acid, so that can break up into ammonia and H plus. Would be an ionization or dissociation. In Chem1B, what we're going to do is this. Because H isn't so stable, and in Chem1B, it's nicer to see the whole reaction. We're going to take our ammonium and react it with water. Well, you know, there's already water present because this is aqueous, this is aqueous, and this is aqueous. And we know H plus is so unstable, it's going to react with water to produce hydronium. In this case, we'll just do it once. Ammonium plus water gives us hydronium plus what? NH3. So both of these equations say the same thing. The top equation is more compact. The top equation is the way I would have done in Chem1A. But in Chem1B, we do it the bottom equation way. And the bottom equation way, this is hydrolysis. Hydrolysis is when you react something with water. Hydrolysis of water is breaking apart the water, but it doesn't have to break apart. You know, something gets added to it in this case. And so when we have weak acid, we have partial ionization, partial dissociation, or partial hydrolysis. So it's partial ionization, dissociation, or partial hydrolysis. And so we have water around, water's base. Actually, water is both an acid and a base. And let's take a look at the reaction here based on our strength chart. So when you look at ammonium, what's its rank? It looks really weak, doesn't it? Ammonium is a really weak acid. It's pretty low in the ranking here. And we're reacting with the base water. In terms of the water's ranking, it's also very low because on the right side, the top is down here. And so this is also very low. It's pretty weak. And so if we take ammonia, react it with water, is that a pretty steep climb? Yeah, that's a pretty steep and long climb. You know, in other words, here, this is not a very simple reaction. Because what's happening here is we're taking a weak acid, in this case, and a weak base. And when we react those, the product of it will be what? So if we take ammonia and react it with water, we're going to form hydronium. Well, hydronium is a much stronger acid than ammonium. You know, this is many, many levels above. Is that mine? Sorry. Many, many levels above. And then we are going to form what else? Ammonia. And so the end result here is this. We go from a weaker acid to a stronger acid, and a weaker base to a stronger base. Ammonia is a stronger base than water by a lot. So is this very favorable? No. Not liquid. Okay, so it's a pretty steep uphill climb here. Now, does that mean that the entire population of ammonium and water, none of them have enough energy to make it up the hill? None of them? None of them? It doesn't mean that. What it means is that the population is going to be very small. You know, the population to make it up this steep hill is going to be very, very small. But what we want to do is we want to figure out what is that population. In other words, we want to do the stoichiometry of this, because if this is too steep of a hill to climb, then we have no reaction. But we know that weak acids have partial reaction. And so what is that population that can make it up that hill? And the population that can make it up the hill, we're going to use some Chem1B stoichiometry for that. Let's take a look at the we're ignoring the chloride for right now. Okay, so what is, can you write out the Gibbs expression for this? And then tell me how we're going to get the K expression. And let me pause this just for a second. Okay. Okay, well, let's do it. And concentration of NH4. All right, so what we can do is we can get an idea of what this is going to end up as. You know, we're going to see how much we're going to have equilibrium. So this is what we're going to do. We're going to weigh out 0.1 moles of this. So we get the molar mass, we figure out how many grams of that we need, it's 0.1 moles. And then we're going to dilute it to 1 liter. So we're going to have 0.1 molar ammonium chloride. When we have 0.1 molar ammonium chloride, it's going to dissolve and then ionize or dissociate. And then the ammonium, being a weak acid, will partially react or partially ionize. And so some of that 0.1 molar will hydrolyze to form some hydronium and some ammonia. And so this is the way we set it up. Initially, I'm starting off with 0.1 molar ammonium chloride because that's what I mixed together. But I know that some of that ammonium will actually react. Well, when I first mix it, none of it reacts. So I'm going to have 0 molar and 0 molar here. I'd like to use moles. You know, normally when we do stoichiometry, moles, mole ratios, but does moles give us the same pattern, the same law? You know, if I use moles, is that okay? And the answer is I could use moles here, but at the end I'd have to calculate molarity because this ratio only works for molarity. It does not work for moles. And so this might look a little weird doing it in molarity, but that's the way we do it. Okay, so there's going to be some change. You know, a little bit of this is going to react. And so at the end of this, I'm going to have a little less of this. I have to figure out how much I'm going to have. And so at the end of this, I'm going to have some ammonium that's going to be the equilibrium, what we call the equilibrium amount, because, you know, I don't know what it is, maybe it's 10%. Let's say if 10% of it reacts, then I'm going to be left with 90%, so 0.09. Or maybe it's 20%, you know, I'm not sure what it is. Now, does the molarity of water change? No. And so we ignore that. Molarity of hydronium could change, but what's going to happen is some of this will hydrolyze water to form some hydronium. Well, how much? That's what we want to figure out. And so we need the hydronium at equilibrium, and we'll also need the chloride at equilibrium. And so once we have these values, we can plug it into the K here and see what that ratio comes out to. And so the first part of today's experiment is we're going to measure K. How are we going to measure K? The way we're going to measure K is by measuring these. If we measure these and then plug it into the equation, we can calculate K. And so how can we measure the ammonium? Like, for example, I know how much I put in there initially. I just weighed out 0.1 mole and then diluted it with water to get 0.1 molar. But then I already know some of that's going to react. And so I need to measure this at equilibrium after it's reacted, once it's stabilized. And so I've got to figure that out. Think of some way. Maybe we could take advantage of the chemical properties of this or something. We need to measure out how much hydronium and how much chloride we have at equilibrium. That's not so easy, actually. Well, actually, it's not so easy for ammonium, and it's not so easy for chloride. These two would be pretty hard to measure. I mean, we could try precipitating out the chloride. If we tried precipitating out the chloride with what? What would precipitate out chloride? Well, actually, this is wrong. It's not chloride. What is this? It's supposed to be NH3. Sorry about that. Yeah. Okay, good. You weren't tripping. I was tripping. Here. It's not chloride. It's NH3. Sorry about that. Well, that's not going to work. Well, I don't know. I don't know how we're going to measure those. You know, we might try to take advantage of some redox or something, but you know, both of those are reducing agents. It's going to be kind of a challenge. Except for one of these. One of these is really easy to measure. Do you know which one? Hydronium. Yeah, but pH. This one's easy to measure. And this is how we're going to do it. And so at least we can measure one of those pretty easily, hydronium. And that is, we're going to use a pH meter to do this. And so the first part of the lab is determining K experimentally. And so if we take a pH meter, we can get the pH of this, and then we know the definition of the pH. Definition of pH, or the equation for pH is, the pH is just equal to the negative log of the hydronium ion concentration at equilibrium. And so this will measure for us the hydronium ion concentration at equilibrium. And pH is going to depend on how much hydronium. I mean, nothing happened. Let's say this was too steep of a climb and we got no hydronium, then we shouldn't get any hydronium here. And so we're going to see how much hydronium we actually get. Do we expect very much? I don't expect very much because that was a pretty big climb right there, but we'll check it out. And so once we measure the pH, and then we calculate the hydronium. Okay, so the first part of the lab is to get some 0.1 molar. It's already mixed up. Somebody made some solution. It's in that last hood there on the back wall. And so we're going to get some of that. But before we get that, we need to check out some equipment from the stockroom. You need to check out a pH meter and some additional glassware. So go ahead and grab it from the stockroom there. We'll start. You can work individually or you can work the probe tip. On the outside surface of the glass bulb is a membrane, a gel membrane. And the gel membrane is very sensitive to hydronium ions. So if we build up a concentration of hydronium ions on the outside, and we compare that to the positive charge on the inside, we could create what's called a voltage. That is, if there's more charge buildup on the outside of this than on the inside of this, positive charge, we're going to set up what's called a voltage or an electrochemical potential. That voltage is going to be sensitive to how much hydronium gets stuck on the outside of this. So the more hydronium, The higher the voltage, less, I think, the lower the voltage, something like that. And so this is going to be how we're going to detect the hydronium ion concentration in here. The first thing we need to do is we need to make sure that this is reading correctly. That is, how do we know we're getting an accurate pH from our pH meter? And we don't. And so what we do normally as a first step is we do something called a calibration to make sure it's reading correctly. But before we do the calibration, let's just go ahead and try to measure a pH of something that we know what the pH is. And we're going to measure the pH of these solutions. We have this one here and this red one and the green one. The red one at 20 degrees C has a pH of 4.00. And today it's about 20 degrees C. The green one at 20 degrees C has a pH of 7.02. And so what we're going to do is, what's the current reading on your pH? Okay, so let's read the red one here. And so you have a couple of little plastic beakers. What you need to do is you need to pour in enough of this is called a buffer solution. Buffer solutions are kind of expensive, so don't use too much. We just need enough to cover the bulb, the glass bulb, completely. And so like a centimeter height or so. Okay, so go ahead and come up and grab some yellow and red solution here. Yeah, that's right. So these buffer solutions aren't very hazardous. The red one has some acetic acid and some sodium acetate in. And the green one has some phosphate, dihydrogen, monohydrogen phosphate in there. So it's not very hazardous. Don't put it in yet. Unless you did this. Did you wash it? Don't put the probe in there yet. What we're going to do is whenever we do this, we don't want to contaminate these solutions. And the conditioning solution will contaminate that solution. So what we have to do is we have to get a big beaker. And the big beaker is going to be your waste beaker. And so get a big beaker out of your drawer and get some fresh DI water in a wash bottle. So it's fresh DI water, just dump out what's in there and just refill it with some fresh DI water. It's just grab a bottle there. Oh, no, it's all right. Or actually, that was in the storage solution. What was the pH of your storage solution? Yeah, that's all right. Okay, so rinse off the bulb. In fact, we want to keep the bulb hydrated at all times. It's a gel membrane. If the gel membrane dries out, it makes the pH probe very unresponsive. And you have to rehydrate it, which takes time. So thoroughly rinse off the tip of the probe with DI water. Now it's wet with DI water, but we don't even want to contaminate the buffer solution with DI water. And so we're going to get a Chem1B and dry the tip of the pH probe and the bulb as best you can. Okay, once it's clean and relatively dry, then put it into the red solution, which is the pH 4, and then just stir it. keep stirring it until you get a stable pH. Do you have a stable pH? Yeah? No? Oh, what is it? 3.88. Okay. Anybody else? 4.10. Okay, so in the calibration, yeah, you should have a stable live voltage. It shouldn't be changing, even if you mix it. And then type in 4.00 for value 1. And so what this is telling us is, what it's telling the LabQuest is, for this voltage, that corresponds to a pH of 4.00. Okay, then hit keep. Okay, now we're doing a 2-point calibration. And so the process is rinse, dry, and then put it into the yellow-green buffer solution. So rinse, dry, then place it into the yellow-green and keep mixing it until you get a stable voltage, until the voltage doesn't change. Okay, my voltage came out to 171. You had 174. What did you guys have? 172? 170? Mine seems to be stable. How about yours? 173 now? Stir it, because if you don't stir it, then it changes gradually. And you're going to be waiting for a long time. So if you stir it, it'll hopefully speed up that process, reaching a stable voltage. All right, mine looks pretty good. Once yours looks pretty good, what are we going to put in here? We're going to input 7.02. According to the bottle, that's what the pH should be. 7.02. And then we keep it. And then click OK. All right, the next thing you're going to do is you're going to take a small beaker and get about 30 or 40 mils of ammonium chloride in the hood, the last hood over there. And we're going to measure the pH of that. Okay, after you get the ammonium chloride, you're going to follow the same procedure. Wash the probe, dry the probe, and then measure the pH of ammonium chloride. And wait until you get a stable pH. All right, so we do the calibration step to get rid of any systematic errors. So for example, if you go to the gas station and you fill up your tank with gasoline, you want to make sure you're getting a gallon worth of gasoline, right? You don't want to be getting like 0.9 gallons if you're paying for a full gallon, right? And so they got to calibrate those. Scales at supermarkets need to be calibrated. The county will do that. But for whenever we do an experiment, the first step we do is calibration. That gets rid of systematic error. So if the pH meter is reading too high all the time or too low all the time, we want to fix that. There's another type of error that we really can't fix, and that's random error. Have you heard of random error versus systematic error? Random error are these natural fluctuations. Sometimes it's reading a little high, sometimes it's reading a little low. What's that? I don't know. That's weird. Okay. Yeah. So one way to prevent or to minimize random errors, one way to prevent random errors is to take an infinite number of measurements. If we take an infinite number of measurements, then half of them will be too high, the other half will be too low, and then they'll even out. We aren't taking an infinite number of measurements, so we take as many measurements as we can. And based on statistics, what's the optimum? You know, the optimum number. Is there an optimum number of measurements? Well, there is sort of an optimum number. This optimum number is to try to minimize the number. We want to do it in as few as possible, but we want to get the maximum benefit. And do you know what that is? And so typically when we do a science experiment, we do 3 trials, you know, because 3 trials has what we say is the, 3 trials, if we take a 4th trial, it's better, but how much better? You know, so if we do 1 trial, it's not very good because you're really subject to random error. 2 trials is much better. 3 trials is a lot better. 4 trials is a little bit better. And so it's a lot of like diminishing returns. So if we do, let's say 1,000 trials versus 1,003 trials, do you think it's going to make much of a difference? You know, 1,000 versus 1,003 is not going to make much of a difference, but, 1 versus 3 makes a huge difference. And so we're going to see the biggest return there. And so fortunately, we have 3 trials here. And so we're going to just average these 3 trials. So 5.00, what did you guys get? Okay, 5.32. And what's the other trial here? 5.32. 5.22? This? Okay. So we have 3 trials. Okay, which of these 3 trials is the most accurate? Well, we don't know. You know, maybe the first one is and the rest aren't, or maybe this is. You know, we don't know. So the best thing is just to take the average of the 3 trials, and that's what we're going to do. We're just going to take the average because we don't want to guess which one's the most accurate. And so we can do that with Excel pretty easy. And so I'm going to equal average of these 3 trials. And so the average pH of these 3 trials is 5.18. But in science, whenever you do an average, we want to have some kind of indication of the spread and the number of trials. You know, let's say 3 trials, yeah, I just told you 3 trials is kind of the optimum, but if we did 30 trials, that would be better. It just takes a lot more time, right? And so can we tell how many trials this 5.18 is based on? No. We can't. That could just be 1 trial. And so there's no indication about how many trials. Can we tell what the spread is? That is this 5.18 the average of, let's say, 4.18, 5.18, and 6.18? That has a pretty wide spread. Or is it the average of, 5.17, 5.18, 5.19? That has a very tight spread. Can you tell by looking at the average if the spread is very wide or if the spread is very narrow? You can't tell. And therefore, in science, we need to be able to tell if that was a wide spread, if that was a few points or a lot of points. And what we're going to do is we're going to take the average, and then we're going to calculate something called the 95% confidence interval. And I'll talk about what that. In order to get 95% confidence interval, I need to get standard deviation. The standard deviation is like a 68% confidence interval. I'll talk about what that means briefly. But to get the standard deviation for this, Excel equals standard deviation. We have different standard deviations. It's probably hard to see. Standard deviation P, standard deviation .f, standard deviation A, standard deviation P. We're going to use the .s, standard deviation for a sample. For example. And so the standard deviation is 0.16. And so this means this. If we took an infinite number of measurements, the average would be the true value, the actual pH. But did we take an infinite number of measurements of the pH of ammonium chloride? We didn't. So we're using some statistics. And the statistics is modeling this based on a distribution curve. And that is this. What this means, the standard deviation here, what this means is that 5.18 plus or minus 0.16, the significance of that range is that we predict with 68% probability that the true average lies within that range. But that range is not broad enough because if it's like 68%, 32% might be outside that range. So what we're going to do is widen it until 95%. So that's called confidence. So Excel can calculate the confidence interval. This is confidence.norm using normal distribution. We're going to use a t. This is called the student's t here. So confidence.t. What parameters you should use are. When we put in confidence.t, we have to put in three parameters: alpha, standard deviation, and the size. Alpha, we could have different, like we could have 90%, we could have 95%, we could have 99%. The standard in science is 95%. And so most people will report it in terms of a 95% confidence interval. And to get 95%, that means 0.05 is out. 5% is out. And so alpha is going to be 0.05, which is going to give us a 95% in. And so 0.05, comma, and then the standard deviation we just calculated. I'm just going to click on that cell. And the size. The sample size, we did 3 samples. Yeah. And so I'll type in 3 for that. And 0.41. This is our 95% confidence interval. All right, so this is what that means here. What that means is this. You look at the range here. And so we got a pH. The pH is 5.18 plus or minus the 95% confidence interval, 0.41. So what this means is this. What's 5.18 minus 0.41? 18, 23, 4, 4.72, and then plus that would be 59 to 5.59. Okay, within this pH range, 4.77, okay, thank you. 4.77 to 5.59. Okay, so within this pH range, there's a 95%, we have 95% confidence that the true average is here. You know, we can't get the true average because we're not taking an infinite number of measurements. So based on some statistics, come up with this range. True average. The true average is the actual pH. Is in this range. Now, how can we narrow down that range? We can narrow down that range by taking more measurements. We can narrow down that range by, trying to be more precise in the measurements. If we have a large spread, it's not going to be very precise. So, for example, let's take a look here. If I do this. So if I double the number of samples, look what happens to my 95% confidence interval, 0.15 versus 0.41. So it's much, in other words, we can have more confidence in that. Likewise, if it's more precise, that'll narrow the range. However, if it's less precise, that won't. So let's add or change some of these. So now I have 6 data points, but here let's say one of them is 7, which is kind of out there. Look what happened to my confidence interval. Here. Let's go with a 3 here. I didn't change the average much. If I look at the average 518, 513, it didn't change the average much, but look at the spread now. The spread goes all the way from 3 to 7. Do you see that? And then take a look at the confidence interval. It's quite wide. All right, so this is our data for this experiment here, and normally in science, we're going to write it like this. This is the average plus or minus the 95% confidence interval. Okay. Next, what we're going to do is our calculation here. Now, if our pH was 5.1, what is hydronium concentration at equilibrium? And so let's do that calculation next. So I'm just going to use some properties log and then solve for the hydronium ion concentration at equilibrium. The hydronium ion concentration at equilibrium is going to equal the anti-log, base 10 minus 10 to the minus pH molar. So this is going to be 10 to the minus 5.18 molar, which is equal to, let's get it standard scientific notation. 6.60 times 10 to the negative mole. Now, what do we do with the sig figs? This is what we do with the sig figs. When we have a power function, pH is the power of the hydronium ion concentration. Whenever we have a power function, whatever is after the decimal are sig figs. So this is 2 sig figs. And that holds for any power function. All power functions are sig figs. After anything before the decimal is just power. You know, this is like the exponent here. And therefore, this is not significant, just like the 5 would not be significant. This is between 5 and 6. This is between the power of 6, because if we go to 10 times 10 to the minus 6, 10 times 10 to the minus 6 is 1 times 10 to the minus 5. So the power is between 5 and 6. 6.61? Okay, that's fine. 6.61. We're only allowed 2 sig figs, but often what I do in calculations is I carry an extra digit. I carry an extra digit to avoid rounding errors. Sometimes I'll carry more than an extra digit. Okay, so we have 6.1. And let's go ahead and enter that here. I want to calculate K. So we have one of these, this one, here. This is equal to 6.61 times 10 to the minus 6 molar. Okay, we don't put the units in here when we calculate it. And so that leaves 2 more to figure out. And so the next thing we have to do is we have to figure out how much ammonium we have and how much ammonia we have. How should we do that? Let me ask you this. Do we have to measure the amount or concentration of these two? Actually, no, we don't have to measure the amount or concentration because we can figure it out using math and stoichiometry. So try to figure out what these concentrations are based on the stoichiometry of this reaction, Chem1A style stoichiometry, and then see if we can calculate the K. So give it some thought and see if you can figure out how to get the other 2 concentrations without having to measure it. Okay, the ammonia concentration, what did you get for the ammonia concentration? The same concentration? Okay. Did anybody get anything different? 5.0 times 10 to the negative 2. Okay. Now this, Chem1B and Chem1A stoichiometry are different, but in certain respects they're similar. And so let's say if I lost 1 mole of ammonium, and this reaction went to completion, how much hydronium would I form? 1 and 1. I have to form the same amount of hydronium as ammonia because they're all 1 to 1 to 1 mole ratios. So if I lose 0.1 moles of ammonium, then I would expect to form 0.1 moles and 0.1 moles. But I don't know how much I lose because I'm not going to lose 100%. I don't think lose 100% of this for strong acids. Strong acids ionize or dissociate 100%. So if this were a strong acid, then it would be easy. 0.1 moles would go to 0.1 and 0.1. But weak acids are harder because weak acids, we don't know what it is. We call it minus X. So if I use minus X molar, how much hydronium will I gain? Well, it's a 1 to 1 mole ratio. So if this is minus 1x, we're going to have plus 1x. And this is also a 1 to 1 mole ratio. This will be plus x. And so what we're doing is we're going from 0 to 6.61 times 10 to the minus 6. That tells me that Well, these must be the same. Does that make sense? But that leaves us this, how much ammonium do I have left over? Yeah, and so this is going to be 0.1 minus 0. Now I need 5 zeros. 1, 2, 3, 4, 5, and then 6, 6, 1. And then I'll add some zeros up here. And so doing this, I'm going to get 0.09999339. 339. Is that what you guys got here? We plug, okay, now I have the equilibrium concentrations because we were able to measure this one and then figure out what. In fact, what we can do is we can get the percent change. You know how we get the percent change is the percent change is going to be the change over the initial. So let me go ahead and calculate that here. Percent change is equal to the percent reaction, which is equal to the percent ionization, which is equal to the percent dissociation for an acid, which is equal to the percent hydrolysis. And to do that calculation is, well, it's how much I lose. How much did I lose? Did I lose all of it? If I lost all of it, that would be 100%, right? But I only lost a little bit. And so the little bit that I lost is this. It's going to be 6.61 times 10 to the minus 6 over the original 0.1 times 100%. So I barely lost any of it, actually. And so the percent dissociation is going to be quite small. In fact, it's going to be 10 to the minus 1 gives us 10 to the positive 1, 10 to the minus 5. 10 squared would give us 10 to the minus 3. So this comes out to 6.61 times 10 to the minus 3%. Or in other words, 0.0066% reaction. That's not much. But we didn't expect much reaction because remember it was quite a steep climb uphill. And so there's a very small population that can make it up there. But can we use this to predict other ones? Let's say I change it. Let's say I go to 1 molar. Will I have the same percent dissociation for 1 molar versus 0.1 molar? What do you think? Will it be the same percent reaction if I change this to 1 molar? You would think so, but you know what? It's not the same. Let's say I go to 0.05 molar. If I go to 0.05 molar, will I have the same percent dissociation, same percent reaction? The answer is it's not the same. Remember what the early chemists tried to do is they tried to find a pattern, and the pattern wasn't the percent reaction. Percent reaction didn't work. What worked? What worked was K. And so let's calculate K because that works. And so if we calculate K, it's going to be, 6.61 times 10 to the minus 6 squared divided by 0.0999339. No units. K, really, there's no units here because K should be expressed in terms of activity. And activity is dimensionless. And so let's go ahead and do this calculation. I'm going to get 6.61 times 10 to the minus 6. Square that. Divided by 0.099999339. So I get 4.36 times 10 to the minus 10. What did you guys get? 4.36 times 10 to the minus 10. So rounding this to the sig figs, I get 4.4 times 10 to the minus 10. You got the same? Okay, good. So this is experimental determination of K. And then lots of groups do this. Lots of groups do this and they average it. And do you know what the accepted value is for this? The accepted value is based on a bunch of averages. We average all of them. The accepted value came out to 5.6 times 10 to the minus 10. So we're off a little bit. But we're off a little bit, is it because of what? Well, it could be due to experimental error, or it could be due to other things. For example, the ammonium solution is only 1 sig fig. And so we have to worry about another type of error. Another type of error is this. We can express things plus or minus the confidence interval, but when we take measurements, we usually express those measurements in terms of plus or minus the maximum error. And so it boils down to this. You know, the stocker up here made that solution. And so how precise, how accurate did they make that solution? Do you think they spent all day, maybe all week, making sure that solution is right on 0.1? That was 0.100000000 molar? No, because if we only have 1 sig fig, then when we express that in terms of maximum error, that will be plus or minus. Usually it's plus or minus like half the smallest unit. In other words, when I see 0.1 to 1 sig fig, I think of a range. The range is going to be between 0.095 to 1.04. All of these will round 1 sig fig to 1 sig fig as 0.1. And so we can see, I mean, this is, 0.14 rounds to 0.1, but that's like a 40% error. You see that? And this is like a 50% error. Or is it 5? Yeah, 50, well, whatever. It's a big error. And so if that solution is slightly off, if it wasn't so precisely and accurately made, then that could also be the reason we're off here. Because if we look at the percent error for this, let me calculate the percent error. Yeah. The percent error is going to be the experimental minus the theoretical, or accepted, divided by the theoretical times 100. And so that's going to be 4.4 minus 5.6 divided by 5.6 times 100. And so we're looking at about 21.4% error. Or about a 21% error. Okay, so there are things, that could have led to those errors. All right, what we're going to do next is we're going to use the case to do some stoichiometry, to do some calculations. And so what we want to do is we want to be able to do stoichiometry calculations to predict, how much we should form or what the pH is going to be. And so that's determining K. The next step is we're going to be using K for stoichiometry. So what we're going to do is our ammonium chloride, we're going to do 1 to 2 dilution. A 1 to 2 dilution of the 0.1 molar will make 0.05 molar. So we're going to put ammonium plus water yields hydronium plus ammonia. In this case, we're going to start off with 0.05 molar, so half as concentrated. Are we going to see 0.0066% reaction here? No, we aren't. We aren't. We're going to see a different percent reaction for this. But here we're going to use the accepted K. We have a choice here. We could use the accepted K value, or we could just use our K values, experimental. In certain respects, using the experimental K value would be more appropriate here. Using the experimental K value would be more appropriate because we could have a systematic error. And the systematic error could be the concentration of our original ammonium chloride is off. If the concentration of original ammonium chloride is off, that means K is one. If K is off, then what we should use is the experimental K value here. And so let's do that. Let's use the experimental K value. Because what that means is we're using the same solution to make our dilution, so it would be more appropriate to use this. And so we're going to use 4.36 times 10 to the minus 10 here. Okay, now H2O is a pure liquid, and what we're going to do is we're going to take our original 0.1 molar and dilute it in half. Okay, the way we're going to do the dilutions is we're going to use a volumetric pipette. So we have a 5 milliliter volumetric pipette, but we need 20 milliliters of solution. The 5 milliliter volumetric pipette, we need to clean this. So one way that people do this is they'll just rinse the inside with the wash bottle like this. Okay, so we can do that. We'll rinse the inside, make sure there's no solution contaminating this. Let's see. This one's leaked there. Okay, there it goes. Okay, and then what I do is I just rotate it and then just drain it from both sides. So rinse this out like maybe 3 times. Okay. Okay, then we're going to get a clean beaker here, small one. And then you're going to put 2 5 milliliter aliquots in there. We should use a 10 milliliter, but we already had the 5 milliliters out. Have you guys done pipetting before? If not, then you need to get practice because you're going to have to be pipetting later. And so we're going to be doing 4 pipetting, so everybody should get a chance to do pipetting. And to do pipetting, you have a pipette bulb, squeeze the air out of the pipette bulb, and then gently put the bulb on top of this, and then put it into the liquid here. And so let me do that. And what's going to happen is we're going to suck up the water in here. So I just got a beaker of water, but I don't want to suck it into the bulb, so I remove it from the bulb quickly and then cap this. So the meniscus is here. I need to lower the meniscus until it gets to the line. To do that, I'm going to just gently release the pressure on the lid, on the top here, and then just let it go down. If I overshoot it, I got to put some more in there. So I overshot it. And squeeze this. Draw some more liquid in here. And then I'd like to use my thumb. A lot of people say don't use your thumb. And I don't like to release it. That is, I don't like to lift it and put it back in. I just like to relax it and then let it flow. And then once it hits that line, I squeeze it down. So now the bottom of the meniscus lines up with the etched mark. You should see a white etched mark in the glass. And then transfer it to a clean beaker, dry beaker, like this. I'm sorry? DI water. So first, wash it with DI water, and then we're going to transfer it to DI water because we don't know what was in here before. So that's why we're washing it. Okay, mine has drained, but there's still one drop of liquid left in here that's not coming out. There's one drop of liquid that's not coming out. Should I squirt that in here by just blowing some air through it? So if I blow some air, watch the tip, there's a drop or half a drop. And the thing is, it depends on the type of pipette. This pipette is a TC pipette. You can see it's marked TC on the neck. TC, oops, it's not marked TC. What is yours marked? Do you see it under the 5? It's a T, it's not TC, it's TD. Do you see a TD marking? So look under the 5 mLs and it should say TD. Okay, TD means to deliver. It's been calibrated to deliver, so leave the little drop in there. You know what TC stands for? TC means to contain. So if it's a TC pipette, you squeeze, you blow the remaining liquid out of there. If it's TD pipette, you leave it in there. It lasts a little bit. Okay, so we need 2 pipettes. Those are aliquots, 2 pipettefuls of DI water. That's 10 milliliters of DI water, 10.00. And then we need 2 pipettes of ammonium chloride. But the problem is, how can you dry the inside of this? One way you could try to dry the inside is blow air through it, but you aren't going to dry it. So is there some other way to dry this? You could try putting it in the oven, but putting this into the oven, it softens the glass and changes the volume. We don't put volumetric glassware in the oven. So we aren't going to be able to dry it. The way what we're going to do instead is we're going to wash the water out of here. So now this is contaminated with DI water. And so what I'm going to do is I'm going to pour some of the ammonium chloride into a waste beaker. Actually, say this is my waste beaker. And then I'm going to use a few milliliters to rinse it. So now I have water in here. I put some ammonium chloride and I wash the inside surface of this to get rid of the water that's contaminating it. And so I do this like 2 or 3 times. So that's one rinse with ammonium chloride. And then another rinse with ammonium chloride. And then maybe another rinse, not full. I don't go all the way to 5 milliliters. I just put 2 or 3 milliliters in there. Okay, then once I do that, then I'm going to go back to my ammonium chloride solution over here. I have 2 separate ammonium chloride, one for rinsing, the other for the experiment. The one for rinsing, you know, because when I put the pipette in there, a little bit of water will get in there and contaminate it. And so what I'm going to do is I'm going to go back to my fresh ammonium chloride, that is here, and then pipette 2 5 milliliter aliquots into my beaker here with the water. And so what results here is what we call a 1-to-2 dilution. A 1-to-2 dilution means 10 milliliters of ammonium chloride were diluted to a total volume of 20 milliliters. 20 milliliters would be the 10 of the DI plus the 10 of the ammonium chloride. And so that's a 1-to-2 dilution. A 1-to-2 dilution cuts the concentration in half. And so that we have the original concentration, which gives us 0.05 more. Okay, but what we're going to do is we're going to calculate this first and then measure the pH. And so let's go ahead and calculate this first and then measure the pH. Do you know how to calculate it? Tell me how we can figure out what the equilibrium concentrations are here. Well, the way we're going to figure out is we're going to lose some. So this is going to be minus x. Over here, this is going to be plus x. And this is going to be plus x. And so at equilibrium, I'm going to have 0.05 minus x molar. I'm going to have x molar hydronium and x molar ammonia. The molarity of water doesn't change, so we'll leave that out of there. And then I'm going to plug this back into the Kc equation, and so I'm going to have this. The hydronium concentration at equilibrium times the ammonia concentration at equilibrium divided by the ammonium concentration at equilibrium. I don't know what those are, but I'm going to plug in here, x here. So I'm going to get x squared on the top, and then 0.05 minus x on the bottom. And this is going to equal 4.36 times 10 to the minus 10. And then just solve this for x. When I solve this for x, let's go ahead and do that over here. I'm going to get this into quadratic form. So, getting this in quadratic form, I'm going to get x squared k plus 4.36 times 10 to the minus 10 x, and then 0.5. What's 1/2 of 4.36? It would be 2.18. So this will be minus 2.18 times 10 to the minus 10 is equal to 0. Well, actually, I need to change that. It's 0.05. And so 4.36 times 0.05. Let me just do that. 4.36 times 10 to the minus 10 times 0.05. 2.18 times 10 to the minus 3, 6, 9, 10, 11. 10 to the minus 11, sorry. Do you like solving quadratic equations? No. Neither do I, and this is why I recommended the calculator. Well, if you don't have the calculator, you can do this online. So I'll just use this online quadratic equation so far. We'll plug in A. A is just equal to 1. B is equal to 4.36 times 10 to the minus 10. 4.36 E minus 10. C, negative 2.18 times 10 to the minus 11. Negative 2.18 E negative 11. Okay, so I plug in my A, B, C, and then hit calculate. So here are my x. I have plus and minus 4.669. 4.6 times 10 to the minus 6. It cannot be minus. We can't have a negative concentration here. It wouldn't make sense. So this has got to be plus 4.668 times 10 to the minus 6. So this is 4.668 times 10 to the minus 6 molar. All right, so that should be the hydronium ion. We can figure out the other concentrations as well. But if I had this, then the pH is going to be equal to the negative log of this concentration. 4.668 times 10 to the minus 6. So let me go ahead and calculate that. .668 times 10 to the negative 6. Take the log of that and then change the sign. So I get a pH of 5.330. How many sig figs are we allowed? We're only allowed 2 sig figs here. And so we're allowed 2 sig figs here. And so the pH is 5.33, which would be 2 sig figs. Okay, that's our prediction. Let's check our prediction by experimental measurement. And so what you're going to do is you're going to do the solution dilution for the ammonium chloride. 2 pipettes of DI, 2 pipettes of ammonium chloride. And then mix and measure the pH. When you measure the pH, it's the same thing. Wash with DI, dry, and then measure. And let's see how close we get to our predicted pH here. All right, so go ahead and give that a shot. Let's see. And so if that's the case, there's something in statistics called a Q-test. The Q-test allows you to throw out data. And so we do a Q-test. If it's too far out from the mean, we'll throw out the data.